In the last video, we worked exclusively with predicates that produce a specific output for a given input. So these predicates were deterministic. However, we did hint at the possibility of predicates that were not deterministic, and that concept is explored more thoroughly in this video. As before, we will be dealing with both Prolog and Mercury code. On the left, we have Prolog, and we have a predicate called smaller than that has a value v. We have a list that must have at least one element, and we see that there is an underscore here. What this underscore means is that we don't care what that value is, and therefore we will not give it a name. This is important to do to avoid warnings that point out so-called singleton variables. Usually, when a variable only occurs once in a predicate definition, that means that it was a mistake. At the very least, it means that that variable will not be related to any other variable and therefore could be literally anything. If you know that this is the way your predicate is supposed to behave, then it's good to put an underscore there so you don't get that warning. Otherwise, the compiler thinks that you're making a mistake because you probably meant to relate that variable to something else. But here we don't, because we really do just want to get some value from this list that is less than this value. I don't want a specific value, just any value. But how do I define that in general? Well, if the first value is less than that, so the first value in the list is less than v, which is what we see here, then the result can be that first value from the list. We could also recursively search through the tail of the list, xs, and notice that in this case, I don't care what the name of the head of the list is. I leave that as an underscore. So either the first element is less than this value, or I recursively process the tail, which will, of course, use this check again to see if any of those values are less. And there is no case here for the empty list, because if the list is empty, then I can't get any value less than v. There's nothing to compare to v in that case. So this is a fairly simple predicate definition. Let's see what happens when we load it up in the Prolog interpreter. So I can ask a question such as smaller than 5, 172635540, and then I want the result. So I press enter on this query, and it says the result equals 1. However, my cursor is still here. That means that Prolog has more answers to give me if I want it to. So instead of pressing enter, I'll press space, and it says result 2. Well, that is also an element of this list that is also less than 5. And if I keep pressing space, I'll work through all of the elements in this list that happen to be less than 5, all the way to 0, which is the last one. I press space at this point. It says false because there are no more. Now, I could also have queried and then press enter afterwards, and then it would stop right away. Because when you press enter into the interpreter like this, it assumes that you're satisfied with the answer you found. You're done looking at different possibilities. And this is really the power of logic programming, is that you can write things in what we call declarative semantics that just get all the answers without having to explicitly define an iteration process or a sort of a collection process over those values. Now, we still need a way to collect and make use of this variety of answers, but I'll first talk about this example in Mercury before I get into that. So as you can see, the Mercury code is identical, except that we have to add this sort of signature that makes it very explicit that we have an integer value that is an in-mode parameter. We have a list of integers that's also an in-mode parameter, and we have another integer that will be an out-mode parameter. So we're going to produce an integer from an integer in a list of integers. But what we see that's new here is that this predicate is non-deterministic. And the reason it is non-deterministic is, one, because there are multiple possible answers. We already saw that with the Prolog example. And two, because it can possibly fail. So if I give an empty list as the second parameter, that would not match any of the patterns I provided and would therefore be a failure. And so that is what non-deterministic means as a determinism mode in Mercury. There's a similar mode called multi, and the multi mode can also produce multiple answers, but it is guaranteed to succeed. It'll never fail. So that's the difference between non-deterministic and multi. So as usual with Mercury, I can't just test this predicate in isolation. I have to have some more code up here that provides a main predicate that'll actually call it. And another interesting thing here is that the determinism mode of my main predicate also had to change. In the previous video, it was deterministic. Now it is something called CC multi. The CC in CC multi stands for committed choice. So what we are saying here is that I'm going to define code that could, in theory, produce multiple different answers. However, I'm going to commit to the first answer I find and ignore future answers. And so that is going to be required to make this particular main definition execute. I'm calling the predicate defined below. I say if smaller than 4, and then some list of numbers here, then I have a result. And this will succeed because that list is not empty. So we will actually print out what that result is. The true here just allows the main predicate to succeed even if this were to somehow fail. We know that it's impossible for this to fail, but because this is defined as a non-deterministic predicate, in terms of the static analysis that Mercury does, at least has to consider the possibility that it might fail. And then this just prints a new line here. So we'll compile this and run it. And it simply outputs 1. So 1 is the first element in this list that is less than 4. So that's a bit underwhelming. What if I want all the answers the way that I did in the Prolog interpreter? And then even in the Prolog example I showed, it was only giving me one answer at a time. So there's still a question of how do I get all the answers and make use of them as part of a bigger program. So I've added some code to this main predicate. And this solutions predicate comes from an import up here. And getting all of the solutions in Mercury and also in Prolog requires understanding the use of higher order predicates. This is a similar concept to functional programming. Higher order just means that we have, in this case, predicates that take other predicates as parameters. So I have this predicate named solutions, and its first parameter is itself another predicate, and then we're going to get a result collection of answers here. Now notice that the smaller than predicate that is being used here as a parameter is only taking in 2 parameters itself, in contrast to the 3 that are expected in this signature below. That's because the required type of the predicate that solutions takes is a predicate with only 1 out parameter. So the fact that that third parameter is missing here means that it will be filled by different possible outcomes, which will then be collected into the list that is this collection here. So let me compile and run this, and then I'll show you something that maybe will make that a bit clearer. Run it. And now this first print here is what gives me that 1. And then the second print here, printing out collection, gives me -3, 1, 2, 3. It's worth noting here that the solutions predicate automatically sorts the output. There's other variations of this that are defined in the solutions module that don't sort it or that given answer as a set rather than a list. And so you can explore those on your own. But what we see here is a list that contains all the elements of that original list that are less than 4. In order to make more sense of the type of parameter that's expected here, let me show you an equivalent version of this code. So we can define anonymous predicates in Mercury. These are similar to lambda expressions that you see in functional programming languages. And the way I would do that is I use the word pred, and then I will say I have a single parameter that I'm going to name x, but its mode has to be out. And this is a predicate that will be non-deterministic. And then I can provide that predicate's definition here. Now, the definition of this anonymous predicate will simply be to call this named predicate, but what's different now is I'm going to explicitly put the x here, because in this context, this is a call to a predicate as opposed to a parameter. When it was a parameter a moment ago, it was okay to leave that final parameter unspecified, and in fact was necessary to match the required type signature of the solutions predicate. But now that I am making this anonymous function, this is just a normal predicate call, and so I have to fill in all parameter spots as expected, like usual. But it also clarifies what is expected here. But the point here is that, this is non-deterministic, this is non-deterministic, so that matches. All that's different is that I filled in the first two variables by providing them here. And what is important here is that solutions will fundamentally focus on predicates that produce multiple solutions. Like, it wouldn't make sense to have a deterministic predicate here because you'd only ever get one solution out. So there's no reason to do this unless you at least have the possibility of getting multiple solutions. Now, because this is non-deterministic, I could have complete failure, in which case collection would be an empty list. Or it could be a list with only one answer. But that depends on the details of the inputs. In principle, it's a non-deterministic predicate, meaning it can either fail or produce multiple different solutions. And so that's what I have here. I can compile and run this code. It'll give me the exact same output as it did before. I've simply sort of changed the way I've passed in this predicate parameter. In Prolog, the most similar higher order predicate to the solutions predicate that Mercury has is the find all predicate. It is still a higher order predicate. Its usage pattern is a bit different. So I have a main predicate here, and I am not just calling find all. I also have a bit of code that calls smaller than in isolation. This is to copy, what I have in the Mercury version. And so the Mercury version called smaller than and gave the first result, and then it had a separate call that printed out all solutions. So I'm doing the same thing in the Prolog code, but here I don't have to have any unusual conditional checking around smaller than. If I call this predicate in that way, I'll simply get the first result and then I'll write it. However, the reason I have this exclamation mark here is this is what is known as a cut. And this is to prevent me from printing out those other solutions, because Prolog doesn't have the strict moding that Mercury has, and therefore it leads you to need to do this kind of wonky management of the determinism or the management of multiple answers in some cases. And so by having this cut operator here, it prevents us from ever going back and finding alternative answers to this predicate. And I'll show you what happens without that in a moment. But first, I want to talk about find all. So it's kind of similar to solutions, except I have to explicitly say, I have 3 parameters rather than 2. And so I have here a call to smaller than that has 4 filled in. It has this list filled in, and then I have x. And so I have to specify that there. Why is the x over here? So what this definition is saying is that I'm going to call this predicate x is an unbound parameter. And then I'm saying here that I want to collect all the different values that x will take on. So x is the focus of what I'm finding all the solutions for. And then specifically, collection will take on the list of values of x that get produced by this predicate call. And then I print it out, and then I have a new line. So I can run this in the Prolog interpreter. I just type in main, period there, and I get 1, and that comes from this call here. And then I get the list 1, 2, 3, -3. Notice that the find all predicate does not sort the output the way that solutions 1 did in Mercury, but they're the same answer. It's just in a different order. And then it says true because overall that predicate succeeded. What happens if I remove this cut operator? I'm running main again. It gives me the same output it gave me a moment ago, and then ends in true, but the cursor is still hovering there, so I can run this again. I press space, and then this is kind of showing why I wanted that cut operator there in the first place, because what it does is it goes back to the beginning, finds a different answer for result that satisfies this, namely the 2, because 2 is smaller than 4. But then it also goes through the rest of the computation again as well, and I get this same answer repeated. And so if I keep pressing space, I have 1 in all of the list, 2 in all of the list. Now I have 3 in all of the list, and then -3 in all of the list, and then finally it fails. So the cut operator prevented me from repeating that over and over again. Now, in some cases, you might want to, but usually when you're defining a main predicate, you want to have a single sort of output stream as opposed to a collection of different outcomes. Now, since we're talking about higher order predicates, I want to take the opportunity to show another way of computing this same answer. And so I've added some code here. I have a very simple predicate, smaller, that simply indicates if A is less than V. And note the order there, it's reversed from what I present here. And then I have another predicate called all smaller than that is going to give me all of the solutions that are smaller. Basically, I could have defined this using find all, which is essentially what we did up here, but I'm going to show you a different way to do this with a different higher order predicate, namely include. Include in Prolog handles the notion of filtering. So I have this predicate smaller that has 2 parameters, but here I'm doing something similar to what we saw in the Mercury syntax where I'm leaving out a parameter. So just different predicates behave different ways. This one is letting us sort of slice off a parameter the same way we did in the Mercury code. So although smaller has 2 parameters there, here I only define 1. The idea being that this parameter slot of the include predicate expects a predicate with 1 parameter, which is this second one there. And I'm going to apply that predicate to all the values from the list XS individually, and then save only those that satisfy the predicate in another list called result. So you can see down here that when I call all smaller than, I call it with the same parameters, the for that list, and then a final one that will correspond to the collection that's being gathered there. And so when I run this, I get the same answer twice. So the first is this collection that's being written from find all, and the next one is the list of another, which comes from all smaller than. I can do something very similar in Mercury. I just have to provide more details. I have a smaller predicate again. In this one, both integers are in mode parameters, and so I'm simply going to either succeed or fail. And this one is semi-deterministic because if I give it the wrong integers, it's not going to be the case that A is less than B, so that will fail. But if I give it others, it'll be true. But That's the only outcome. So semi-deterministic. And then I will define all smaller than. And in this case, that integer is an in parameter. The list of integers is an in parameter. The filtered list of integers is an out parameter. This is actually deterministic. And in this case, the name of the predicate I'm using is actually called filter in Mercury. And Mercury explicitly expects that this first parameter is a semi-deterministic predicate of a single parameter. But other than that, it looks pretty much the same as the Prolog code on the left. I just changed the name of that predicate from include to filter. So once again, a lot of similarity between these languages. And above, I've changed the main predicate code to properly test this. I call all smaller than with 4 in that list. Now, I'll compile and run this. And one interesting contrast here between the output we see from Mercury and the output we were getting from Prolog is that the Prolog output gave the exact same answer for both of our definitions. Here, the contents of the list are the same, but the order of the elements is different. I mentioned earlier that the solutions predicate we're using there sorts the output, but this approach we're doing here with filtering doesn't sort the output. So that's the reason it's different. Once again, there are ways around that, but essentially we're doing the same operation. What's important is that we're collecting a list of all the elements that satisfy the concept of being smaller, and order is a secondary concern. So that wraps up the topic of logic programming. There's much more that could be discussed in the context of logic programming, but I think that the main thing that it can do that is just so different from other programming paradigms is this concept of collecting all solutions to a problem without really having to go into too much detail of how you're going to process and collect and store them. The predicates themselves are simply non-deterministic, and then there's some built-in support for getting all the solutions, which is a very nice, elegant feature that is common across logic programming languages.